I'll begin. Verse for the day, I suppose, Romans 3:23. For all have sinned and fall short of the glory of God. So it's a reminder of where we all start, you know. Anyway, I'll begin with a word of prayer. So, dear Father, we thank you for this day. Again, I thank you for this class. And these students, just pray that you'd just give us understanding today to understand more about your creation, about linear algebra and eigenvectors, Lord. In your name I pray, Lord Jesus. Amen. So, you guys got any questions about the mission? Feel free. You have a few minutes. Yep.
On 62, I was not sure exactly what you meant by the analog of the identity.
Well, you've just shown that the distance from the origin in the old coordinate system and the new coordinate system is the same. Is that also true for your other problem? Like if you, generically speaking, say, like let's just forget about the previous problem, let's just talk about the question in general. If we let y equal to the coordinate vector of x, right, which would be beta inverse times x, right? Is it true that y transpose times y is equal to x transpose times x? Or is that something special to that problem? If you look at your previous problem, is it the case? See, because like y transpose times y is the sum of the coordinates squared, right? This is nothing more than a sneaky way of writing the length of the vector y squared equal to the length of the vector x squared, see? Is that true for general coordinate changes? The answer is no. It is not. That's a special thing that only is true for orthonormal coordinates. There is an easy way and a hard way to do problem 62 also. I'll just mention that.
Yes.
Yeah. The easy way is to do it in general. The hard way is to do it for the problem I gave you. But anyway, other questions? 67. Number 67. So for number 67, something I've told some of you guys is it's nice to prove a lemma. So you're up against t of x is equal to ax plus b. And you end up looking at basically t of q minus t of p, like that's what happens. And if you look at that, that's aq plus b minus ap plus b, right? Because we're just putting x equals to q and x equals to p in the formula. But notice that if we do that, and that just leaves us with a times q minus p. And if you just notice this identity as a starting point, and also very important, do not start on the left-hand side of what you're trying to prove. Start on the right-hand side. You want to begin with the distance from t of p to t of q, right? And then equals stuff, steps, and then distance from p to q, right? Like you start here and there. Doing it the opposite way would make it like way harder. Does that should be helpful if you're stuck currently on it. If I write much more on the board, I will solve the problem. Seriously. Other questions? So the idea of this problem, by the way, is that if your transformations like ax plus b, what you're doing, if you can imagine this, is pictorially, you know, you got some coordinate system, right? You got some points p and q, right? So if you multiply them by a, you're like rotating them. You know, you're like rotating them somewhere, all right? That'd be like AP and AQ. And then you're translating both of those the same way, right? So like maybe over to here, plus b. Now this is not a proof or anything, but this is an explanation for why the distance between the points is maintained. It's because you're rotating around the origin and then you're shifting. So the distance, the displacement between the two remains the same. But you're proving it algebraically, not with a heuristic picture. These are the transformations which preserve the notion of like congruence in the sense of high school geometry. Two shapes having the same size and shape. Admittedly, I do have to add the condition that the determinant of A is equal to 1 in order to make sure I'm not ripping things inside out. But other than that. But I didn't do that because that's not the problem. Other questions? Some of the ones you need to read the book. Like the homework is just like you need to read the book to find out what the shear is. It's not hard, right? Those problems should be pretty straightforward. I just didn't take class time for it because I would end up lecturing for that on 30 minutes, and at the end of that you'd been like, oh, I could have read the book for 5 minutes and got the same, you know. So I think those are good for me to lecture on, honestly. But it's good for you to know about the idea of shear. Other questions? So you guys probably just are not done yet because, of course, it's not due today. But one thing I might mention that's interesting to think about. This doesn't. I don't know if this really has anything to do with your homework per se, but as we think about possible dimensions of things, there's a rank nullity theorem that we talked about before, right? So let's just talk about this for a second. Again, not really the homework, just something that's been on my mind. If we're talking linear transformation from Rn to Rm, right? Notice that like the kernel of T is a subspace of Rn, and the image of T, or the range of T, is a subspace of Rm, right? So what does that tell you about things? It tells you that the nullity of T is less than or equal to n. It tells you that the rank of T is less than or equal to m, right? But these things are also like, they're bound together by the rank nullity theorem, right? The rank nullity theorem says that the rank of T plus the nullity of T is what? It's equal to n, right? So that means that you can't have a rank bigger than n, right? And you can't have a kernel. You can't have a rank bigger than n. You can't have a nullity bigger than n. And among other things, this means if you're mapping from like a two-dimensional space, the most you can get out of that is a two-dimensional image, a two-dimensional range. If your input is three-dimensional, the most you can get over here is three-dimensional, even if you're mapping into a 10-dimensional space. Well, I just wanted to say a word or two about that. The other thing I might mention to you guys is problem. I spotted that I told you guys in the announcement 1/√3 for problem 71. That's important because with that modification, transpose becomes inverse. Let's see here. And then problem 73, what I would recommend for problem 73, and if you did it a different way, it's all cool. But this is what the people I've talked to, I've said, think of it this way. T of x is equal to ax, and let A be equal to A, B, C, D, E, F, G, H, I. So that's going to give you the template for an arbitrary linear transformation from R3 to R3, right? And then look at the data that you're given for problem 73. You have where one vector maps and where another vector maps, right? So if you think about that, those two pieces of data that you're given in problem 73 amount to 6 equations in these 9 unknowns. The data given implies 6 equations for your A, B, C, G, H, I, right? And so you can take those and write them out, and that gives you this big old colossal 6 by 9 coefficient matrix, right? And you can look at the 6 by 10 augmented coefficient matrix, row reduce that thing, and that will tell you the answer. That will tell you how to write the non-pivotal variables in terms of the pivot variables in terms of the non-pivot variables, and that will give you the parameterization the problem asks you for. That's one way to solve this problem. There may be a more clever way, but I haven't found it yet this week, so. It's annoying. Oh, and by the way, you are free to use technology to do that row reduction. In fact, let it be known, going from this point on, you can use like Maple. Well, you guys don't have Maple. Mathematica. No, you don't use that. What's it called? The MATLAB. You can use the MATLAB or a website or something to do the row reductions if you do so choose in the homework. However, caveat, you know yourself. You know if you need practice. And I think it's especially important going forward that you work out a bunch of the characteristic equations, because if you don't do that by hand, you won't be ready for my test. You need to be able to calculate characteristic equations fairly quickly in the next test. You need to have confidence about what you're doing there. If you're just relying on the website to do it for you, you'll be in trouble. All right? So you can use technology on the homework going forward, and I won't take points off for using it. Just use it responsibly. Don't handicap yourself like on the next test, right? So, in the sense of golf. Let's see here. I mean, does that make it better or worse? I don't know. I'll shut up. Okay, so that's that. So eigenvectors. Let us talk about eigenvectors. Now, first of all, why on earth do we call them eigenvectors? Well, there's a bit of a history here. Mostly it has to do with World War II. In particular, World War II, listen to me, World War II sort of stopped the German domination of world mathematics. But you remember Gauss was German, right? And there were significant German mathematicians between, say, 1850 and, I mean, there still are, but so much of the world's scientific progress and mathematical progress was happening in Germany before World War II. And then something unpleasant happened there, and they kind of lost all that, right? And we gained it. That's really the rise to prominence of some of the more elite universities in America happened because we got all of the German scientists and so forth. And give or take, this is the history. But in the early 20th century, Germany was big in terms of its role in influencing the shape and structure of mathematics, bigger than it is now. And that's when this term was born, eigenvector. Around the same time period, I guess, probably. I'm actually not sure how old this term is, honestly. I don't know the history of it entirely, but I'm pretty sure it's German. And so there's that. Now, if you read my section 6.1, I give some motivations for it. There are different motivations. The one is the one I showed you last time, which is that they naturally allow us to solve differential equations. All right, so they appear in the solution for differential equations in a very natural way. They also appear if you study what's called a stochastic matrix. So a stochastic matrix is a matrix that the sum of the entries in any column adds up to 1. That corresponds to the preservation of the probability of a certain state vector. And if you study stochastic matrices, basically the way it works is you have your input state, you multiply it by a matrix, and then you get your next state. So like state 0 leads to state 1. Then you take state 1, you multiply it by the matrix, you get state 2. So like what I'm talking about is the nth state is equal to the stochastic matrix A times the n minus 1 state. And you keep doing this. This is the story of stochastic matrices. And eventually, if there's like a stable point, what happens is that your input state and your output state is the same in the limit as n goes to infinity. What is that? Well, that's an eigenvector. See, if you have x star is equal to ax star, that makes x star eigenvector with eigenvalue lambda equals to 1. You can also say it's a fixed point of the linear transformation that has matrix A. So that's another motivation that would lead you to eigenvectors and eigenvalues. There are many. Let's get into it. So here we go. If A is an n by n matrix, then lambda, I'll give the definition I give in my notes, which is lambda in C is eigenvalue of A if the determinant of A minus lambda I is equal to 0. Moreover, if U is not equal to 0 and A minus lambda I times U is equal to 0, then U is eigenvector with eigenvalue lambda for A, all right? Also, let's say that W sub lambda is equal to U in Rn such that A minus lambda I rather, times U, oopsie doopsie, equals to 0. Just get that out there right now. That's this is called the lambda eigenspace. So you can look at the set of all eigenvectors. It's the eigenspace. All right. So here's a fussy thing. The lambda eigenspace has mostly eigenvectors with one exception. So this is actually important. It's actually very important. A good metric for whether or not you're doing things right actually is here. So remark, U equals to 0 is not an eigenvector. I hope you don't mind that I'm abbreviating it E vector because I get really tired of writing eigen after a while, as you will as well. So 0 is a solution, right? 0 is always a solution to A minus lambda I times U equal to 0, right? Like if you look at this equation, let me just erase the U and put an X here to make you feel different about it. Right? There. Same equation, same idea, different notation. If I put X equals to 0, it solves this equation, right? However, 0 is not an eigenvector. As you're working problems, if you find that your alleged eigenvalue only gives you the 0 solution when you work it out, this means that your eigenvalue is not really an eigenvalue. It means you've miscalculated the characteristic equation. All right? So let's get to some examples, yeah? Oh, I guess there's one theorem I need to mention before we get into the examples. So this is the theorem. Give me a second here, I'll find it. All right. So, like I said, section 6.1, I would love for you guys to read section 6.1, just so you better understand some of the motivations for eigenvectors, but nothing in 6.1 really help you with homework per se, all right? That's just a motivational section. And you might not find it very motivating. That's okay. So, here, the following are equivalent. The following are equivalent for A in Rn by n and lambda in L. So when I say lambda complex, I mean that that could either be real or complex, right? I'm not insisting it's a genuinely complex number, although technically every real number can be viewed as such. Like, is the number 1 a complex number? It is. Is the number 1 a rational number? It is. Is the number 1 a number mod 2? It's also that. I mean, although technically these are different notions of 1. They say there can be only 1, but that's not true. Let's see here. Lambda is an eigenvalue, although that's a pretty good fictional universe. Lambda is an eigenvalue of A. Number 2, there exists V not equal to 0 such that AV is equal to lambda V. Number 3, there exists V not equal to 0 such that A minus lambda I times V is equal to 0. Number 4, lambda is solution to determinant of A minus lambda I equals to 0. Number 5, the matrix A minus lambda I V times V equal to 0 has infinitely many solutions. All right. So equivalent conditions. Lambda is an eigenvalue. There exists, like basically 2 and 3 are different ways of saying there exists an eigenvector. We can either look at an eigenvector as a vector that when you multiply the matrix times the vector, you just get back a scalar multiple of the vector, right? That's kind of different than what we were talking about in problem 67, I guess it was, right? There, when I took the vector and I rotated it, I didn't get back a scalar multiple of the vector, right? I got an entirely different direction altogether, right? So it seems like rotations might not have eigenvectors, yeah? Or do they? No. And then here, so basically 2 and 3 are different ways of looking at an eigenvector, and 4 and 5 are saying that the eigenvalues, well, this basically number 4 says that if you have a solution to the characteristic equation, it gives you an eigenvalue. All right? There's no time that you can solve the characteristic equation and say, fine, get lambda equals to 5 as a solution, and yet somehow not have a lambda 5 eigenvector. That cannot happen. There's always at least one eigenvector for each eigenvalue. And in fact, if there's one, there's infinitely many. Right? If there's one eigenvector, there's infinitely many. Do you see why this is? Check this out. If we have AV equals lambda V, then what happens if you look at A times CV? You get C times AV, right? Which is C times lambda V, which is lambda times CV. So in other words, if V is eigenvector, then CV is eigenvector. This is a fundamental lemma. A fundamental lemma is that eigenvectors never come alone. All right? If you're in a battle against an eigenvector, you better bring friends because he's got infinitely many. You know? So anyway. And then this is just the characterization that, if you have one eigenvector, you've got infinitely many, which is what I just told you. All right, so let's work some examples. So example 1, here I have A equal to 3, 0, 8, minus 1. One criticism I have of my current set of notes is I do not take maximal use I don't take maximal advantage of the determinate identities that I developed in these notes. Like, if you judiciously use the row operation determinate simplifying things, you can make additional calculational improvements on the things I do in these notes. I don't know if I have anything like that to show you today, so I'm not going to try to make it up because bad things will happen if I do that. But here it is. So our goal at the moment is to find the eigenvalues and eigenvectors for this matrix. So step number 1, you look at the determinant of A minus lambda I. Now, listen, guys, we got a choice to make here. You can either look at this equal to 0, or you can look at this equals to 0. Why do I choose this rather than that for this course? Like, this is more theoretically beautiful. Just bar none. Like, this is much nicer theoretically speaking, because it gives you a leading coefficient of lambda to the n. I mean, the leading term in the polynomial is lambda to the power n. This gives you a leading term of minus 1 to the n times lambda to the n. But the nice thing about this is you only have to put minuses on the lambdas, and the matrix stays like it is. I just found, after teaching linear algebra for years and years, that students make less mistakes if you don't make them put a minus on every single entry in A. There's just more opportunity for mistakes with this one, computationally. So that's why I do this. It's nothing exciting. You could go either way, though. And so like last class, if you look back on it, you'll notice that I did this last class. But here it goes. 3 minus lambda. I think I did. I could be wrong. 0, 8, minus 1 minus lambda. There's my determinant. Multiply this, we get 3 minus lambda, minus 1 minus lambda, minus 0. All right, so that is, listen, get rid of the minuses, right? It's just better. This is minus lambda minus 3 times lambda plus 1, right? So what are my eigenvalues? So we get lambda 1 equals to minus 1, and lambda 2 equals to 3. As a general rule of thumb, if we can, it's nice to make like lambda 1 less than lambda 2, just to give it an order. That is not a requirement. That's just a, custom, like using a salad fork or something, That's really outside my experience. I don't believe in salad. Except for Caesar salad at the Texas Roadhouse. I'll allow that one. Although I'll tell you, there's nothing sadder than when you get that and it's like hot. Every so often you don't get the chilled plate. You just feel like you just want your money back, Because it's so much better with the chilled plate. Like, it's just so much better. Anyway, I digress. So we found our eigenvalues. Great. Now what? Let's look for the eigenvectors. So, eigenvectors. All right, so we're trying to solve, and I usually, as a point of organization, put my lambda 1 equal to minus 1 here, tell my reader that's what I'm doing. So I'm looking at A minus a minus I, right? Times U1. In other words, I've got, let's see here, 4, 0, 8, 0, and then let's say UV. So as a general nomenclature, I like to use UV for the disposable variables that express my eigenvector. So my eigenvector I'm looking for is U1. I'm just letting U1 to be UV. Right? What's the solution here? We need what? We need 4u equals to 0. The second equation gives me 8u is equal to 0. Apparently, u is equal to 0, right? So therefore, u1 is what? 0v. So how many choices are there for v1? V not equal to 0, right? We can't let v be 0. So now, I don't like to have a whole family here. So I'm just going to say, so choose u1 equals to 0, 1 for the sake of specificity. That's a good choice because that makes the vector have length 1. All right? Could you make another choice? Absolutely. You got infinitely many choices to make. There's just one tree you cannot eat the fruit of, and that's the tree of the v equals to 0 fruit. Like v equal to 0, it's no bueno. That means it's not good. Lambda 2 equal to 3. So we got ourselves a minus 3I times u2. All right, so that gives us, whoa, dude, 0, 0, 8, minus 1, minus 3, minus 4 uv. Okay, so the first equation there tells me nothing, just nothing. The second equation tells me that 8u minus 4v is equal to 0, which tells me that that tells me that v is equal to like 2u, right? So therefore, u2, generically speaking, has the form u 2u for u not equal to 0, right? So completely ad hoc choice on my part. I'm going to choose u2 equal to 1, 2. Other popular choices include u2 tilde 1 over the square root of 5, 1, 2. All right? In the website I'll share with you guys, you got choices. Either you can get the website to normalize your eigenvectors to have length 1, that would be my u2 tilde choice, or you can pick your eigenvectors to have integer entries, maybe. That's the 1, 2. I like integer entries, no fractions, yeah? So guys, that's it. That's how you calculate eigenvectors and eigenvalues for a 2 by 2 matrix. Now, technically speaking, if the eigenvalue lambda is complex, that makes the corresponding eigenvalue a complex eigenvector. And I won't really talk about that until after break, but I wanted to allow for it in the definition. So just a warning. Not everybody does that. Some people insist that the eigenvalue of a real matrix be real, and that's fine. And then they just have a special separate definition for a complex eigenvector. Technically, a complex eigenvector is the eigenvector of the complexification of the transformation, which is something I'll blather on about for like a full day or two in 321. But in here, I'll just say that. So there's an example. Now, we could do things with this if we wanted. All right? But let's go on to another example, as I have devoted other days for what we can do with it. At the moment, I'm just going to focus on how to calculate it. So example 2, let us suppose, oh, this looks nice. Maybe this will be easy. This is almost too easy. 2, 3, 4, 5, 6, 7 zeros here. Let's see how this goes. All right. So let's find the eigenvalues. The determinant of, a minus lambda I is what? 2 minus lambda, 5 minus lambda, 7 minus lambda, and you got your minus 3, and your minus 4, and your minus 6. I'm going to put some dividers in here because it looks kind of a little bit, numbers are getting a little bit too cozy. There we go. And don't want to have to send out an email. Let's see here. And I don't know what I'm talking about. Let's see here. 2 minus lambda, nothing to talk about. 5 minus lambda, 7 minus lambda. Although it does seem like a fun experiment to see, like, could you, no. What would it take to prompt an email at this point about some kind of campus alert? I feel like there's an experiment to be done there, but I don't know. We're not wearing masks anymore, though, so it's really not the time. Yeah. Oh, so apparently the eigenvalues are what? Lambda 1 equals to 2, lambda 2 equals to 5, lambda 3 equals to 7. All right? So those are your eigenvalues. In fact, there's a theorem to be seen here, right? So let me just make a remark. It's fairly obvious that this calculation we just did would work anytime we have a triangular matrix, either upper or lower, or a diagonal matrix, right? If your matrix is, if A is upper or lower, triangular or diagonal, then the entries on the diagonal of A are eigenvalues. Right? The eigenvalues are exactly 257, not an accident. Right? So if we take the determinant of either, if you think about A minus lambda I for a upper, lower, or diagonal matrix, it's still an upper, lower, diagonal matrix. And so when you calculate the determinant, it's just the product of the diagonals. So that's cool, but it's a little bit more than that. In fact, and the standard basis is eigenbasis. What's an eigenbasis? I think that's right. Oh, maybe I'm wrong about that. Maybe, don't write that down just yet. Let's calculate, see what happens. Shut the door for now, I think. See here. It's the sound of students taking my physics test. Sorry, too soon. Some of you are in there. Lambda 1 equals to 2. I'm harmless. My physics is easy. I don't know what I'm talking about. A minus 2i times u1 is 0, 3, 4, 0, 3, 6, 0, 0, 5. And for this, I like to use disposable variables u, v, w. That's equal to 0. What's that tell me? Well, the last equation tells me that 5w is equal to 0. So therefore, w is equal to 0, right? And, oh, and then the next two equations both tell me basically that 3 times v is equal to 0. Because we know that w is equal to 0 in our solution, so the 4 and the 6 go away when you think about it, right? So that just lands you with v equal to 0. And so here's a very popular mistake on the next test that you guys like to make, which is like, oh, well, there's no equation for u. So what's u must be? What must u be? You guys will, and I hope this is not going to be a self-fulfilling prophecy, I'm telling you right now, but there's many of you who, for reasons I don't fully understand, want to make u equal to 0. But the thing is, we have no information about u whatsoever. U is completely free. So u is free. It's not 0. In fact, 0 is the one thing you cannot choose. U is free. So like u1 has the form, generically speaking, u 0, 0. Which means that I can choose u1 is equal to 1, 0, 0. Interesting. All right. The thing I'm stuck on in my brain, I haven't written on the board, so don't be bothered as I'm bothered by my thoughts. As far as I know, you don't have my thoughts, so we haven't given Elon Musk that much power yet. So never sign up for Neuralink. That's all I'm saying. A minus 5I U2. That gives us a minus 3, 3, 4, 0, 0, 6, 0, 0, 2. And these are, so you guys know about, what's the term in computer science when you have a variable and then you like keep reusing it? Like you redefine it and use it again? Whatever that is, that's what we're doing. So like this u, v, and w from the previous step is not the same u and v and w is now. These are just my letters that I use to work out the details for each eigenvector, all right? When we go on to the next eigenvalue, the previous equations are dead to us, all right? And so like this here, the last one tells me that 2w equals to 0, so therefore w is equal to 0, all right? And yeah, that looks like all I'm going to get from the last two rows of the matrix, right? The first one will give me what? So let's take the w equal to 0 into consideration here. We really just get minus 3u plus 3v equals to 0, right? Which tells me that v is equal to u. So therefore u2 has the form u 0. So I will choose u2 equals to 1, 1, 0, just to be, there you go. All right, now on to eigenvalue 7. Lambda 3 equals to 7. We've got a minus 7i, u3. So look, we can now safely do what? Incorrect. Nope. Not true, right? Was the eigenbasis a standard basis? It's not. By the way, an eigenbasis is simply a basis of eigenvectors. All right? So the theory of eigenvectors is very nice. For example, if you have distinct eigenvalues, the eigenvectors coming from distinct eigenvalues are necessarily linearly independent. So like I can be assured that once I find the eigenvector for eigenvalue 7, if I look at u1, u2, and u3 constructed in this way, I know it's going to give me a linearly independent set of vectors. And because we're talking about 3 dimensions, that's a basis. And since each one of the vectors is an eigenvector for A, that makes it a quote-unquote eigenbasis for A. Just saying. Now, what we got? We got minus 5. Where was I? 3, 4, 6 goes here. Minus a 2, 0 down here. And then 0, 0, 0. Again, UVW, but not the same one, right? So it looks to me like this time, so check it out, yo. Finally, something I need to use row reduction for. I have not used row reduction up to this point because it was unnecessary. These problems were so simple, we didn't need row reduction. When do I use row reduction? When it's not immediately clear what the answer is. That's when I use row reduction. So here, I will use row reduction on this augmented coefficient matrix. All right, so what we get then is, I'll write it up here. So we had what? Minus 5, 3, 4, 0, minus 2, 6, 0, 0, 0. And I'll put this over here. I mean, do you need to write that? Not really. But this, let's see here. To make these match up, I'm going to multiply the top one by 3. Excuse me, by 2. I'm going to multiply this one by 3 because I hate fractions. Sorry if you have family that's fraction. See here, but see here. I'm sure they're good people. See here, 0, 26, 0, minus 6, 18, and I think we're done. Well, pretty much we're done. So that is rho equivalent to 1, 0, minus 26 over 10, and 0, 1, minus 3. Right? So what's that tell me? That tells me that u is equal to 26 over 10, w, and that tells me that v is equal to 3w. And so that tells me that the generic form of u3 is, right? Actually, I'm not going to write down the generic form. I'm going to be smart about this. By smart, I mean lazy. As you know, we hate fractions. So we're going to choose w equal to what? I guess I could actually, I hate fractions, but I should at least try to understand them a little bit. You know, so much war comes from misunderstanding. Let's see here. So 13 over 5, yeah? So if I choose w equals to 5, that's a nice choice because then we've got 13 here, and we've got 15 here, and we've got 0 there. Oh, I'm an idiot. W was what? 5. Okay, so there you go. And there you go. So we have found the eigenvalues and eigenvectors for this 3 by 3 matrix. Now, I think you see where this is going. What if the matrix is not nice? Like, what if it's not a triangular 3 by 3 matrix? What are you obligated to solve? What's the nature of the determinant? What's the nature of the characteristic equation? What is this? I've erased the general one. So think about this. For a in Rn by n, if you think about the determinant of a minus lambda I equals to 0, this is a nth order polynomial in lambda. So how do you solve those? The answer is, of course, carefully. Now, so let me just tell you some fun facts at the end of all this. So if we let beta equal to, say, u1, u2, u3, my point is to you that that's difficult in general. Even for a 3 by 3, that's a cubic equation, right? So it requires some care. But if we were to write beta equals this, if we calculate beta inverse a beta, guess what we'll get? Well, I'll tell you what we'll get. We'll get 2, 5, 7. For the 3 by 3, for the 2 by 2 I had earlier, if I make the basis u1, u2, and I calculate the inverse of beta times the matrix that we had in the previous example, I would get the eigenvalues. What were they? For example 1, minus 1 and 3. So you can, this one's easier to work out. You get minus 1, 0, 0, and 3. So this is what if you can find an eigenbasis for your matrix, it allows you to diagonalize the matrix. And there's so much more to say about that in terms of, like, you know, if you can do that, that means you can easily calculate powers of the matrix arbitrarily high and so forth. What I want to alert you to before I go today is that you're not alone. If you go to my website, go to your course website, and right here there is item number 4, eigenvector calculator. I personally prefer the old version of this calculator. You can put in, like, for example, what did we just work out? What was it? 2, 3, 4, 0, 5, 6, 0, 0, 7. And of course there are also, built-in commands. Certainly there are built-in commands for MATLAB, but check it out. That's just what we calculated. And so this is I would urge you to use this to check your work, right? And also, especially when you're calculating the eigenvalues, it is worth it to double check, right? After you multiply out for a more complicated matrix the characteristic polynomial, it's really worth plugging it into here, checking that you actually have calculated that determinant correctly. Because you don't want to go on from there if you've got the wrong eigenvalues. Yeah? Anyway, that's all for today. So, if you guys have to miss Friday, I understand. It's okay. You can watch my video. I will not be offended.